Hello, everyone. My name is Lucas. Today, here to present a joint work from my colleagues from UFIJ Brazil, IMT Atlantique, France, and IISC India. Our work is on load balancing and autoscaling. Both of them are widely used tools for dynamic resource allocation. And in essence, we would describe load balancing as a distributed workload, a common workload across the available servers. And upscaling could be something of adjusting the number of the levels of the service that will serve the jobs. So here we have two figures as an analogy, the supermarket and the toll road. And here, the load balancing could be to designate the clients or the vehicles to the queues. And auto-scaling, if it's a horizontal scale, it could be for creating open or closing queues. Or if it's vertically scale, it could be selecting between an experience or experience employee. But this is just about an analogy. Let's talk about the industry. It's actually being used a lot for companies, especially in the realm of cloud computing, web service, and the routing. And here we can see that we have the two examples of these solutions separated. And the follow-up question that comes is how these two solutions interact to each other. Because our intuition is if we compare a scenario where we have these two separated strategies that don't collaborate with each other, comparing to a scenario where we have an integrated strategy that's coupled these two load balancing and scaling, the former would be less efficient than the latter. So the outline that we bring here and also the contribution for the presentation is we formulate the problem of load balancing and scaling as a weakly coupled Markov decision making. Then we present some insights from how the optimal policy behaves when we change the system parameters. And finally, we will present a learning algorithm that can learn this model even with unknown parameters. So starting with the formulation of the problem, here we have any queues, and each one of them can have a state, which is the length of jobs that are in the queue, and also can have actions. For load balancing, is either to receive or not the job, and for autoscaling is selecting which rate is going to serve between high and low. All the queues are homogeneous, and they have a fixed buffer size of k, and at each time slot, an arrival of size alpha n can occur in the system with probability p. So for instance, if alpha is half and we have 10 queues, 5 jobs will arrive every time slot with probability p. I marked here this queue to serve an example of how can we see the state and action of a queue. We can see that this one is full, is also rejecting, and also operating in high service rate mode. Another way to represent this queue is through this table, where on the rows we have the states, which goes from empty 0 to full k. Therefore, we have k plus 1 possible states. And for the action, we have these 4 possible actions: reject at the low rate, reject at the high rate, accept at the low rate, or accept at the high rate. Here, the green cell can indicate that this queue is full, rejecting at high rates as the previous one. Okay, and what happens when we have n queues? Because each one of them would have this amount of states, k times 4 times k plus 1. And what happens is the problem now becomes to the power of n. And for each of these possible distinct states of the system, we could have a definition for valid or invalid according to the constraints. For instance, in this last state example here, we have all queues operating in a high service rate, accepting, and they are full, which will be an invalid case because you cannot accept if you're full, and also you cannot use all service in high rates. So what would happen if you have a policy distribution over these possible states is that those invalid states would never happen in the distribution, and while the most common ones would have a mass function, a mass probability. And one thing that I think you're also asking is how can we cope with this exponentially growing number of queues? And the way we can do this is instead of using the n queues, we just use one single one as the representative queue for them. So this is a heuristic where we can relax the constraints. And if we compare the original problem with the relaxed one, we can see that it's reduced significantly the amount of states But we have a trade-off here because since the constraints on the previous model, the original model is instantaneous, so the invalid cases can never happen. Here we have the constraints on expectation, so we cannot encode these invalid cases for this scenario. And I know what you're thinking, because this heuristic is also a good representation for the original problem, and it turns out that from recent papers from Nicholas Guest et al., this heuristic is known to be asymptotically optimal in the sense that it converges to original solution as the number of queues grows to infinity. Now, the relaxed problem can be formalized as a linear programming, where we want to find the policy distribution that minimizes the operational costs subject to the constraints on expectations. Okay, but what are these constraints, the operational costs and these constraints? The operational costs include the incentive to accepting jobs, an incentive to reduce the processing, the energy cost, and incentive to reduce the delay. And for the constraints, we have inequality budget constraints, one for load balancing, that the number of queues that are accepting cannot be surpassed the number of jobs that arrive in the system, measured by alpha n, I mentioned here earlier. And for auto-scaling, the number of service rates, operating service rates cannot surpass the energy budget, which here is we're defining is beta n variable. So a last constraint, it's now a quality constraint, is that we have a state transition matrix, because a state transition of the system that needs to follow this P matrix. Because here on the left, we have a state of a queue, which is on the time is what Tn. And on the right, we have the next arrival, which will be happen in the Tn plus 1. So the thing is that the state of the queue is moving from full, rejecting, and to a state that is empty and at a low rate and accepting. And to measure the probability of going from the state S to the state S prime, giving the actions for load balancing the node by A and for auto-scaling the node by B, this P matrix is essential to tell what's the probability to this event occur. If this P matrix is known, we can use it like a library such as convex pi to calculate, to solve this linear programming problem. And that's what we did. So we bring here 3 insights that we have from the optimal policy. The first one, here we have on the x-axis, we have an arrival probability of the jobs. So if it's more frequently, it's increasing they become more frequently. And on the y-axis, we have the normalized high rate use. That is the number of queues that they operate in high mode divided by the number of queues that can operate in high mode. And what we can observe is that as the arrivals become more increasing, the usage of high mode is also increased to the point that becomes active, that is fully utilized. The second insight is that we also have the same y-axis, normalized high rate, but on the x-axis, we have the budget itself. And if we increase the budget, we have a more flexible budget. It does not necessarily mean that it will use all this budget. So the thing is that it's saving the energy costs because of the objective functional constraints. The third insight is that we have a phase transition. Here, we are measuring the rejection penalty on the x-axis. And on the y-axis, we have the normalized acceptance, or that is the number of queues that accepting divided by the number of jobs that arrived. We have observed that below a certain threshold, it practically rejects all jobs, but after this phase transition, it accepts all jobs. Now, to finalize the presentation, we have this learning without unknown parameters. In real-world scenarios, we would not have access to this P matrix. So how could we do? We can estimate it through simulation. So the thing is, first we need to move from a directive method, which is the linear programming, to an iterative method, which is the Lagrangian that encapsulates the constraints into the objective function. And second, we need to apply a regularization term here to make the problem from convex to strongly convex, because since the original problem is a linear programming, it's the gradients of the variables will be constant. And finally, let's see the iterations that in the epoch. We have, first of all, we need to estimate the P matrix, and how we do this is by simulating actions on the current state and obtaining the fraction of those observations that will lead to each possible next state. And with this estimated P matrix, and also the policy and the Lagrangian multipliers, we can give this as the inputs for the Lagrangian function, compute it, and we're using the gradients to the third step, which is updating the policy, doing graded descent on the policy and rate ascent on the Lagrangian multipliers. So the question that remains is it's converging. Here we are measuring the solution. Since we have the optimal policy, we can compare the learned and the optimal one. And we do this with the norm of the Froebel's norm of the two policy, the difference of the two policy. On the left, we are comparing the graded descent ascent using the actual P with the convex pi. And on the right, we are comparing the graded descent ascent with the stochastic graded descent ascent, which is using the P estimated P. So we can see that it's converging as the iteration goes. And I think that's it.